Numeral force free body diagrams. That's the fancy physics name for drawing a picture with forces on it. So we're going to kind of go in baby steps. We'll talk about identifying which forces are there. We're going to talk about the direction of forces, how to draw a free body diagram, and then we'll put it all together at the end. Okay. So starting out, you've got a situation that's listed. This one has a block resting on an inclined plane without sliding, and you're asked if these forces are present. So is there gravity? Yes. So yes, there's gravity. Yep, you can write yes, put a check or X, whatever. Okay. Are there any springs in the picture or the description? Nope, no spring forces. Are there any ropes or cables? Okay, so no tension or ropes, so that force isn't there. Is the block sitting on a surface? Yes. Yes, so that means there should be a normal force. So the actual incline that it's sitting on pushes the block up, it's actually going to be a little bit of a diagonal direction, but it keeps it from falling through that surface. So there is a normal force. And is there friction in this case?
I feel like yes.
There's no sliding though.
Okay, but what's keeping it from sliding?
But if there's no sliding.
So what you're thinking, if it were a horizontal surface and there was no sliding, there wouldn't be friction. But this one, because it's on an incline, the friction's the only thing that's preventing it from sliding down. So in this case, there is friction. Okay, since there isn't any rope or spring or anything like that holding it up and keeping it, friction has to be the force that prevents it from sliding down the incline. Okay. And in this case, it's not moving, so we don't have any air resistance. In that one, there was not.
Why not?
Because it wasn't moving, so there was no wind slowing it down.
Could be some way like going up.
If it were sliding down, then there could have been air resistance.
So if the wind is keeping it from sliding. Wait, it's not sliding down.
Oh, it's not sliding.
Just still.
Yeah.
Maybe.
Okay, so this one you have a block hanging at rest from the ceiling by a piece of rope. Is there gravity?
Yes.
Are there any springs?
No.
Are there any ropes?
Yes.
Is the block sitting on a surface?
No.
Is it rubbing up or being prevented from moving?
No.
Is the wind blowing in its flappy hair?
It's at rest.
It's at rest. No air.
So every time it's at rest, there's no resistance. There's no air resistance, right?
So summarizing, each force is drawn as a vector. The tail end of the vector starts at a point in the center of the object, so all the vector tails touch. And then the direction that you draw your arrow points in the actual direction of the force. So for example, gravity is down, you would draw an arrow pointing down. And then you want to clearly label your forces with the symbols. So they're going to get kind of crowded. Don't bother writing out the words. You want to use your variables. So a capital F with a subscript is the easiest to remember. And then it's okay to draw a set of axes if it helps you to remember X and Y for your coordinate systems. Okay? And since not all of us are artists, sometimes you'll see an object drawn just as a block or a square. You can also just draw a circle, so you might see that as well. So any kind of simple shape can represent the object that you're talking about. And again, all of the forces are drawn from a point at the center of the object. And then we're going to go over what some free body diagrams look like, so you can kind of get a picture in your mind as we go through these. So it kind of summarizes the rules for you at the end. You only draw forces. It's okay to draw a coordinate system. And then all of the forces begin at a point. So let's say I had an object that was just falling and I neglect air resistance. So if I have an object that looks like this, if I were to draw a force vector with gravity pointing like that, or I were to draw it like this, which one of those is correct? The one on the left or the one on the right? The one on the right. Okay. This one is the correct one. Okay. This one is not correct because I didn't start my force until the edge of the object, and you want all of the vector tails to touch. The next slide, you've got some examples of valid free body diagrams. So you can see how all the tails touch in the middle. Okay. So we've got gravity pointing down on all of them. Then all of your forces point in other directions. So you may not necessarily see the entire scenario, like you don't have to draw the surface in or the ropes or anything like that. You're just seeing the forces drawn. And then it's okay to draw coordinates to the side, or you can center your coordinate system in the middle as well. And a reminder, we mentioned this in your notes that you watched. Sometimes, like this one, you might have a force there and you're not sure what exactly is causing it, or it'll just say there's an applied force and you don't know what it's from. So FA is just kind of a generic term for applied force. And in the middle of your page, you've got an example of a free body diagram, and it asks you if it's correct or not, and it actually gives you the answer, so it's like an example that's done for you. This one is incorrect because it draws in a velocity vector, and we only draw force vectors on our pictures. So we're going to go through some examples and kind of mentally go through our checklist together and see if the pictures are drawn correctly or not. So on the next page, you've got two. It says a block suspended from a massless rope. I know that like it technically has mass. It just means it's not going to add any extra weight to it. So you're just using it as a rope, not for the heaviness sake. Okay. So we've got a block. Is there gravity?
Yeah.
Yes. Is it drawn correctly in your picture?
No. Yes. Gravity. Yes.
Okay, the gravity is, so it's pointing down. Are there any springs? Nope, so no spring force. Are there any ropes?
Yes.
Yes, what force is from a rope? Tension. Okay, so this one's here. If you don't like using the capital T for tension, you could replace that and say F with the subscript of a T. That looks like an E, sorry. You should know by now, I'm not that great with the stylus. Okay. So F with the subscript of a T, or just a plain capital T for tension. Is the block sitting on any kind of surface?
No.
Nope, so there's no normal or friction, and it's suspended, so it's not swinging in the breeze or anything, so there's no air resistance here either. So this one would be an example of a correct free body diagram. Mm-hmm. And that's it. By the end, we're going to put all of these things together, and you'll practice drawing them. Okay. So on your second one, you have a book resting on a table. So this one, you draw the table in for you, which is okay, but we're interested in the book. Okay. So just mentally, checklist. Is gravity there? Is it drawn downward?
Yes.
Yes, so that one's right. Are there any ropes?
Nope.
Nope. Any springs? Nope. Oh, but look, they drew a spring force. Okay, so that is wrong. Okay. So our spring force should not be there.
So like, what would a spring look like? A little spiral thing?
Uh-huh.
How do we know it's a spring or a rubber band?
It can be anything that stretches. It can be a rubber band too.
Like, what would that look like? Would it like say there's a rubber band on it, or like?
It would say it's being pulled with a rubber band or being pulled with a spring. So in this case, since it doesn't say anything about that, then you're not going to have any. It is sitting on a table, so is the normal force correct?
Yes.
Yes. So the normal force, it's perpendicular to the surface. So since our surface is horizontal, the normal force is perpendicular to that. That's correct. And it's just resting on the table. Is there any friction? Nope, and it doesn't draw it. So this one, what's wrong was that there was an extra force drawn in. Okay.
What's an end force?
Normal. That's the one from the surface. And I don't know if like SAT, if you guys still do like vocabulary flashcards and stuff. I know normal, we're used to that meaning ordinary, but normal is also an actual synonym for perpendicular. So since the normal force is always perpendicular to your surface, that's why it's called that.
So like normal force is only like, I don't know.
It's like your chair pushing on you. If your chair didn't hold you up, you'd fall through to the floor. This next one, we have a sled pulled along a smooth, frictionless, horizontal patch of ice. Okay. Is there gravity? Is it drawn correctly? So that one's good. Are there any springs? Nope. Are there any ropes?
Yes.
Maybe. Okay. So this one, it draws this as a tension. Does it make sense that you would pull a sled with a rope?
Yeah.
Yeah, so that's okay. If you're not exactly sure, but you know it's being pulled, you could also say applied force, but it does make sense that that's tension, because normally you probably would pull a sled with a rope. Is the sled sitting on a surface?
The ground.
It's on the ground, so what force should the ground place on it? Normal. Okay. So this one's not correct because it's missing the normal force. And since the ground is horizontal, the normal force would be vertical pointing upward. Okay. And is there any friction?
Yes.
Yes.
Read your description.
No.
Oh, frictionless. Okay. So this is where you're going to have to look at the description and the scenario of the picture that's drawn as well. So this one specifically said there's no friction. Okay. So on a test, I might give you a picture like this, and you would say this one's incorrect because it did not draw the normal force. Okay. On the next one, we've got a box being pushed up an incline, and it does tell you, yes, there's an applied force pushing it up, so that one's okay. Gravity is pointing in the right way. Are there any springs or ropes? Nope, because it said applied force, so no tension or spring force. Is it sitting on a surface? Yes, so is there a normal force? Yes. And on this one, I'm going to go to the screen and kind of point a little bit. Normal force is correct. What are you missing in this one? Yeah. See? With friction. So it's missing the friction force. And do you think friction would go the same way as applied or opposite to applied? Yeah. So if we were to draw it in, we would draw our frictional force opposite to the applied force. Friction works against you, so it's always going to be the opposite way that you move. Correct. And we'll look at this a little bit later in more detail, but I wanted to point out where it says constant velocity. In your next set of notes, we're going to look at Newton's laws, and if something has constant velocity, it means that these forces balance and cancel each other out. So if it has friction, there has to be something else to counteract it. So it's kind of looking ahead a little bit, but this one is correct. Okay, we're going to talk about that more after we've done Newton's laws. Okay. On the direction of forces, now if you guys flip the page, we're going to have 8 choices for a given scenario. So when you look up in the corner and you've got these 8 arrows, choices A through H, those are your choices to represent a direction. So up would be A, down would be E, etc. Okay. So here's our picture. We've got a rope attached to a truck, and it pulls a box along a horizontal surface with friction, and it tells you which way it's moving. Okay. So look at your picture. Which way is the rope actually pulling on the box?
No.
Okay, so I'm going to put my little dot in the middle, and the rope pulls this way. That's my tension force. So out of A through H, which one's this closest to? B. Okay, so that's how you would answer a question like that. The next one is the normal force of the surface on the block. So which way is the ground pushing?
Up.
Yeah, up, which would be A. So if I were to draw the normal force, it would look like this. The direction of friction. Good. So it is the opposite way that you're moving. So in this case, that would be G. If you wanted to draw that in your picture, make your vector tails touch, and friction would point opposite to the way that the movement is. And then when it talks about the weight force, that's the same thing as the gravitational force. So which way does that point? Yeah. So that one's going to be down. And then if we wanted to draw in that picture, we could draw it like that. So everything that I just did with these 4 arrows, that's a free body diagram. Okay. So you would go through your checklist, see which forces should be there, think about the direction they should point, and then actually draw those forces pointing in the right direction, and then, wow, you've accomplished a free body diagram. Okay. So that's all there is to it. What?
What's that letter, number D?
E. It's straight down. So So on this one, and I don't know if you noticed the title, but it was like recognizing forces in realistic situations. I don't know who pushes a box along a ceiling. I can't even reach that high, but there we go. Okay. Anyway, so you have these crazy physics imaginary scenarios. So we have a person pushing a box along a horizontal ceiling that has friction. Okay. So it asks you for the normal force of the ceiling on the block. So here's our block. Which way is the ceiling pushing on it? Down. So this one's actually going to be E, because the ceiling is pushing down on the block. What?
So we can like keep an arrow like on the die, like on this part,
Uh-huh.
and like have two different forces.
Yes, so you would just draw one arrow and then label both of them. Okay. So which one were you thinking of that goes that way? Like what else goes down?
Gravity.
Yeah. So if you skip down to the end where we have the weight force or the gravitational force, that one's also E. So if I were to draw them on the picture, I would say the normal force and gravity. So you can label both of them with one arrow if that happens to come up. Okay. The second question asks you for the direction. This is a word, kinetic. We're looking ahead a little bit, but kinetic means moving. But it's still friction, so don't let the extra word throw you off right now. So which way would friction be? Yeah. See where it says moving this direction? Friction's going to be opposite to that. Okay. So it's going to be G. This time we have, it went ahead and called it a normal force from the person's hands. That could also have been an applied force. But which way are the hands pushing? Yeah, up. And this word static means still, okay, but it's still friction. Okay, don't worry about it saying static. Which way is the friction? G again. Okay. And then when it asks you why is the friction of the force of the person on the box static, even though the box is moving, I'm going to show you an example. Two more examples together, so we all get to draw the same picture. This one has a rope attached to a truck pulling a box along a hill with friction. So I'm going to draw my hill. I'm going to draw my box. There's going to be a rope, and it's being pulled by a truck.
It's a really good truck.
Thanks.
Excited about being pulled horizontally, or just that one picture is being pulled at an angle.
So rope attached to a truck. I happen to make the rope even parallel to the hill. So the direction of the tension, we kind of went over this one. This one's going to be B because the way that we happen to draw it, that tension was parallel to the hill. So I would say F with a T right there. Okay. What about the normal force? This one's tricky. Yeah, Nate's got it. So remember that it's perpendicular to your surface. So if my surface is like this and then I tilt it, the normal force tilts with it. So it's actually going to be along direction H, and I would want to draw my normal force like this so that it's perpendicular to the hill. The direction of friction. Which one's opposite to the way it's moving? Yeah, good. Okay. So friction is back down the hill, opposite to the way that it moves. Okay. And what about gravity? Gravity's always the same. There you go. Gravity is always straight down, even if you're on a hill. Okay. So if you ever take a free body diagram quiz, just go label all the gravities first, because it's always there and it's always down. So you'll definitely get that one right. Okay. Doesn't matter that it's on an incline. It doesn't matter if it's hanging or if it's sitting on something. Gravity is always there and it's always down. Okay. So, I know. Oh, we're going to have to finish soon. Okay. So on this one, the way that I might give you something on a test, I would already have the picture drawn for you, and then I would ask you out of these choices to pick the direction of the forces. And then separately, I would say draw the free body diagram, which would be this part right here. So did everybody get a chance to draw in those forces?
Yep.
Okay. So we have one more left together.
Wall of honor student right
That would be a teacher.
Okay.
What is he mad?
Welcome to my world, guys. Okay. He's mad because his keys are in his pocket. You can make him happy because he's like, yay, I'm almost home. It's your person. Whatever facial expression you would like to have is fine. He's like crazy clown makeup guy. I don't know. Okay. Remember, we're looking at one object at a time. We only care about the box. I don't care what expression your little person has. Okay? Forces are going to be the same no matter what the background story is. Okay, battery's getting low. Let's go. Normal force of the wall on the block. Which way's the wall push?
That way.
G. Nice. Okay. Oh, direction of the frictional force on the wall. Uh-oh, you gotta think. If they were to let go, which way would the ball or the box fall? Down, so opposite to that. Up. Friction's up. A. So if you said A before I led you through that, congratulations, that was really good. Okay. When it says could it point another direction, you can scratch that out. It could be side to side, but we don't do 3 dimensions in here. We have another normal force, also could be applied, but they're calling it normal here. The person's hands on the block. Which way their hands push? Good. Hands pushing into the wall. Okay. Remember, there are 2 different surfaces touching either side of the block. So the wall's on one side and the hand's on the other. So what's the direction of friction from the hands? Friction. A. Good, Keaton. Okay. So we actually have 2 frictional forces. One comes from the wall and one comes from their hands. If either side slips, that box is going to fall down. Okay, so you have 2 frictions up there. And then which way is gravity?
Oh,
Always. Okay. So gravity would point that way. So your free body diagram would be those arrows. Good? Okay. It says do a pencil, like use a pencil so that if you make a mistake, you can fix it easily. So just a good idea, looking ahead a little bit. If you cannot draw a straight line with a ruler for, like that far, then I have rulers if you'd like them. You can use your badges, that's good too. Your IDs will work. Okay. So you can use those. Let me get you the worksheets and we'll practice.